So today we're going to be covering 10.5 and 10.6 and working with the Pythagorean theorem and working with determining the area of parallelograms and our process for making that happen. So 10.5, again, getting familiar with the Pythagorean theorem, a lot of this, and it's just showing up again here in 10.5, but it's going to be a review of the section 5.8 material that we covered earlier in the quarter. The general equation that we have for the Pythagorean theorem is a squared plus b squared is equal to c squared. And remember that we need to make sure that when we are working with this thing, we can only use the Pythagorean theorem when we have a right triangle showing up. My recommendations, and we're going to jump over to the actual 5.8 material to see this again in a bit more detail, but my recommendation as you are going through these types of problems, and this is regardless of whether we have been given a story problem, given a generic, here's an A or a B value, here's a B and a C value, whatever it may be, I highly recommend to everyone, draw a picture of a right triangle for yourself. A lot of people do not do this, and then they start plugging in A's and B's and C's into incorrect spots in their equation. So I think, again, this nice little visual of a picture of a right triangle is a really, really long way with that and making these a lot easier. Labeling what we know, what we don't know, and then plugging things into equation to solve after that is our general process for those. So again, I'll jump us over to our 5.8 notes here, because again, this is just a review of that. So again, our general equation is that a squared plus b squared is equal to c squared. And it only works with right triangles. And the giveaway for a right triangle is this little square that's going to be showing up in here. If we do not have this little square showing us that we have a right angle, or nowhere in the problem are we told we have a right angle, we cannot use this equation. Now there are some story problems that we can see, and I think we went through one or two of them. We might have had one or two on the homework. I know they're in the textbook at least, where we are not explicitly told, hey, you're using a right triangle with these. But if we draw a picture for ourselves of the scenario that we are working with, we can see, oh, yeah, a right triangle does form from that. So again, draw that picture for yourself because it's a really, really helpful tool for setting these things up. And again, as a reminder with some of these parts, A and B, these represent the legs of the triangle and they are interchangeable. So the way I have it set up, which is A is the vertical and B is the horizontal, you can reverse these however you would like to. If you want A to be horizontal and B to be vertical, go for it. That's fine. So A and B are interchangeable in our picture. They're also interchangeable in the equation since they're both on the same side, they're both adding together, doesn't matter. C always, always, always must be the hypotenuse of a triangle. There is no exception on that in any way, shape, or form. If you are letting the C value be anything other than this hypotenuse, you're doing it wrong. And we cannot let that happen. So A and B can be changed back and forth. That's fine. C always has to be the hypotenuse. And again, we had our general process for this. Again, draw a picture of the scenario and again, include the triangle of what you are observing. You're going to be given something where you can create this triangle for yourself. I also recommend label that picture and label each side accordingly. You don't necessarily need to plug in values right at the very start. I find it helpful half the time to just say, here's my general triangle. This vertical side represents, maybe it's a telephone pole, maybe it's the side of a house. C could represent, maybe it's a ladder, maybe it's a wire, something to that effect. B could represent the ground, it could represent a measured distance, something to that effect. Labeling these sides in the context of the problem go a very, very long way when you're solving these equations. I think it also really helps then determine, okay, what numbers have I been given in the problem that I'm working with? And where does it correspond in this picture? If I'm told the height of a building is 20 feet, and this vertical side in my picture represents the height of the building, I know where that number goes right off the bat. It takes the guesswork right out of it for me, which is fantastic, and we want that. So once we've labeled everything accordingly. We determined which sides are A, B, and C values, plug them in, and solve for what's left over. And again, we're using the square root to solve what's left over in that problem after simplifying both sides. I think people did quite well. If memory serves me correctly, just about everyone did quite well with this on the test. And again, on Chapter 10's test, or I guess not the Chapter 10's test, but the final exam in all of these, I will be specifying to you guys, or doing my best to specify, round your final answer to 2 or 3 or however many decimal places. Because most of these answers are going to have decimals showing up in them, which is okay, that's fine. And I don't want you guys having to guess at, well, does he want it to 1 decimal place, to 2 or 3? I will specify that for you guys as best I possibly can. But again, make sure you're following this process as you're going through those. Draw that picture. I really, really can't emphasize that enough with the Pythagorean theorem. It's vital to make these problems significantly easier on the homework and on the test. Okay. So again, this is just the 5.8 material, but it's the exact same stuff that we're using in 10.5. It's just coming back because this whole chapter is designed and designated to be around geometry, so we are covering it here as well. But again, reference that 5.8 stuff as you need to. A lot of useful stuff in there. And that's 10.5. So we're going to move on into 10.6, which is working with determining the area of parallelograms. So going back to a little bit of our definitions here of a parallelogram. And a parallelogram is a quadrilateral with opposite sides that are parallel. Again, this is a definition that we had from 10.4. I believe I told you guys when we were working through the 10.4 material that there are a bunch of classifications and a bunch of these different rules that we have for all these different shapes and polygons that show up in these problems. I am not expecting you guys to know the definition of every single one of these different types of shapes. I think that's very unreasonable and not something that's worth your guys' time on it. But I do want to make sure that we have the the definition at least written out for us, that we know what we're working with. So when working with these, again, we commonly have the mix-up, I think, between the perimeter and the area of a shape. And it's a very understandable one because they show up in the problems, a lot of problems next to each other, and some people are taught or get into the habit of thinking that they're interchangeable, when it turns out that they actually are not. So our perimeter of any shape that we're working with, whether it be a parallelogram or something else, the perimeter is the distance around a figure. And we usually determine this by the sum of all the side lengths being added together. So if you were given a parallelogram and you're told, here's a length, here's a length, here's a length, and here's a length, what is the perimeter of this thing? All you do, you just add these things up. If you were given a triangle, if you were given a pentagon, if you were given an octagon, you were told to find the perimeter, and you were given the side lengths. Again, you're just adding all of those sides up. It's the distance around the figure. I think the main exception to this one is the circle, and that has its own special unique way of solving that. But again, we're going to get to those ones later on. The area, and this is the one that we are working with for this section in particular. The area is the amount of space contained within a two-dimensional figure. We always measure the area in square units because we're working with a two-dimensional figure, two-dimensional calculation. We generally, when we are writing those units out for ourselves, we write those out as something to the effect of either square inches. If you write this SQ in, it's implied to be square inches, or inches squared, because we're working with a two-dimensional calculation here. So if you see this showing up in the final answers or showing up on the homework, all that is telling us is that this number represents an area, and we just have to write the units out appropriately for that. So actually getting into and finding the area of parallelograms. So parallelograms, they're slightly different from a square or rectangle. mostly because of the fact that they do not actually have any right angles. So the way that we're going to go through and determine our equation for our area for a parallelogram, it's going to be a slight variation from the square and the rectangle one, in that the equation is instead going to be the area is equal to the base times the height. Now I want to make it clear on this because this is another point of confusion that does show up. It's understandable, but I want to clarify it. The height is the distance directly across from these two parallel lines here. The height is not this length along the side. They're two very, very different calculations. So with squares and rectangles, we could say the area is equal to the length times the width, or the base times the height. The square and the rectangle have that really nice part where we can go and interchange those because the length and the width and base and height are the exact same thing between squares and rectangles. With parallelograms, because they do not have right angles, we cannot just go this length times this length and get the exact same answer. It does not work that way. We have to go the base times the height. The height is the distance directly across from these two lines. You might be saying, well, you said the parallelograms don't have right angles, but you're displaying a right angle right here. And all that this right angle is here to show is that this line, this height, is perpendicular to both of these bases. Basically to show us that this is the direct height directly across from these two things. So when you are going through these, again, identify the base, identify the height, and or the area if it has been given to you. Plug those values that we've been given into the equation and solve for what's left over. So we could have an instance where we were told the base of a parallelogram is, let's say, 2. The height of a parallelogram is 3. What is the area? So we have been given 2 of our 3 unknowns. We plug in what we know and solve for what's left over. So again, a lot of these, and I think this is just the general case with geometry, make these little pictures for yourselves. Make that little visual, fill in what's my base, what's my height, what's my area. And it goes a really long way with these types of problems and how we can go through them and make life easier for ourselves on that front. Now, the next part we have here is estimating areas by scale drawings. And essentially what this is going to be asking for, there's a lot of methods that you can go through to make this happen. Unfortunately, too many for me to tell you guys. Here's the one best one that you can do because, again, there are so many unique scenarios that it's almost on a case-by-case basis which method that you would like to use. But there are a couple commonalities that do show up with these I'm going to touch base on. First and foremost, converting your starting units into the desired ones. If you're working with something that says we're given a drawing in inches that's going to represent a certain number of feet. Which represents and goes back to our proportions back from section 6.2. I think this is a pretty helpful one going back and writing these things out. If we can determine a distance or a length of the original drawing and proportionately kind of scale that up to the actual drawing, that could be really useful. Especially when working with the idea of we've written a drawing down on a piece of paper and we're going to try and scale that drawing to be something realistic. Could be something where this many centimeters on the piece of paper represents this many miles when translated into the real world. And again, proportions would be very, very helpful to help convert those units back and forth and make sure that we are calculating things accordingly. And again, 6.2 is very, very helpful with that. So go back and reference that as we need to. And beyond that, again, we're just going to determine the base, height, or area of the parallelogram, plug in the values that we know, and solve for what's left over. So this unit conversion is probably the only really quote-unquote new thing that we are doing. And really, again, doing that conversion, we're just going to be using the 6.2 material, and we're just going to be using proportions to scale up or scale down a lot of this material. So 3/4 of what we're covering here in 10.6 is just a lot of review. 6.2, it's just review. The new stuff with a parallelogram, again, the toughest part, the part that makes this difficult for people, is not drawing a picture. If you draw a picture, I'm going to put a lot of money on 99% of these problems that you'll have showing up on the homework or on the tests that are going to be like this, you're going to do just fine on. Take the extra time to get your setup correct and draw that visual for yourself, and then plug things in accordingly, and then you're going to be good to go. And yeah, that's kind of everything for the 10.6 material. We only have one page that covers all of it. I don't have any exact examples ready to go because at some point in time it just becomes I'm drawing pictures or I'm giving you guys basically any combination of these things, and you're doing the exact same thing over and over and over again. And again, I think the estimating areas, again, you do a proportion problem at the very beginning, just scale it accordingly, and then apply what we did right up here. There's not a whole lot else that goes along with it. So with that, again, not a whole lot that's particularly new with this. 10.5, a lot of review. 10.6, again, biggest thing I can emphasize, make that visual for yourself. Do a little bit of the extra prep work as necessary, and it goes a really long way. But otherwise, this is everything that we have for the material for today. Again, really quick, really straightforward, I think, in a lot of these ways. So I'm going to end our recording here. And I'm going to open it up to you guys if you want to go through anything with this or any other questions regarding the class or anything else. And we've got a lot of time left, so we can get through hopefully a good chunk of stuff if you guys do have questions. So I'll end the recording here, and we'll take care of that.